Okay, so let's see, how do you approximate a binomial probability by using a normal? So let's look at this. Basically, what we're going to do is we have a binomial random variable, meaning then we know what p is and we know what n is. So we know it might be like 100 tosses of a coin, and the probability of heads is a half, or it could be any variation of these n and p. But anyway, we'll know that. So for example, I think one of the previous examples we had n was 25 and p was 1/5, so that would be another example. But in any case, we know it. Therefore, we know the mean of the random variable. We recall this formula for the mean of a binomial random variable. It's just n times p. We discussed that in a previous video. And we didn't prove it, but you can find the proof, I'm sure. And you can check it out. So anyway, we know n and p, therefore we know mu, according to what we've shown before. And we also know sigma. So what we do is, if we're trying to estimate a binomial with a normal, we'll say we have a normal with mu, whatever n times p was, and we'll have a normal whose standard deviation is sigma, whatever this quantity works out to. And with respect to that binomial random variable, we'll be asking a question like, what's the probability that it is between two bounds? And we'll just say basically the same thing. What's the probability that our normal random variable is between the same two bounds? But we're going to make a slight correction here. Instead of y2, we're going to have y2 plus a half. And instead of y1, we're going to have y1 minus a half. And that's because, remember, we're talking about the histogram. And so the bars extend half in either direction from the y value. So if it's y2, the bar extends from y2 plus a half to y2 minus a half. So that's why we have this half correction. And then after we have that correction, we will say we're trying to get the probability that y is between this will be the probability that x, a normal random variable, will be between x1 and x2, where again x1 is y1 minus a half and x2 is y2 plus a half. So we write it like that, and then we've already learned how to calculate this kind of probability for a normal random variable, and that's the way this is done. All right, let's just read what they say. We refer to the binomial random variable as y. Our objective is to determine the probability that y is between y1 and y2, where y1 and y2 represent numbers of successes in n independent Bernoulli trials. So we might say we toss a coin 100 times, y1 is 50 and y2 is 70, so we're saying what's the probability that we get between 50 and 70 heads, for example. Note, of course, that y must be non-negative. We refer to the normal random variable, which we use to approximate the binomial random variable, as we're going to refer to that as x. The random variable x has mean mu and standard deviation sigma equal to the mean and standard deviation of the binomial random variable it is approximating. So that's what we said. So it's going to be this is mu and this is sigma. The probability that y is between y1 and y2 is the area of the histogram of y between, remember, as we said, it extends the width of each bar is 1 unit long, and it starts at the y value and goes down by half and up by half. So we want y1 minus a half up to y2 plus a half, since the histogram rectangles are centered about integer values. Let's see figure 10. Okay, so here's figure 10. And here we have y1, but we go down by a half and up, and sorry, y2, but up by a half. Therefore, we approximate the area of the histogram between x1 equal to y1 minus a half and x2 equal to y2 plus a half by the area under the normal curve between these same values. Thus, the probability that y is between y1 and y2 is the probability that x is between x1 and x2 given by these x1 and x2. So step 1. Convert the normal random variable x to the standard normal random variable. So this we already know how to do. So we just take x minus mu over sigma, and in this case it's x minus np over this, and then proceed as in the previous examples, meaning look it up in the table. So we get that and when we look it up in the table, we'll be looking this up in the table. That will be equal to the the probability that x is between here and here, and that will be approximately the probability that our random variable is between here and here. Okay, so let's go back to this diagram, which was different binomial random variables. Remember, p was equal to 1/5, so this is not like a fair coin, where p would be equal to a half. And we saw that when n is equal to 5, it doesn't really look like a normal curve, so maybe it wouldn't be a very good idea to approximate this shape, or this random variable, this binomial random variable, by a normal random variable. And even when n equals 10, it doesn't look so good, right? It doesn't exactly look normal. But when n equals 25, it really does start to look like a normal random variable. So maybe when n is equal to 25, we could do this approximation. So we have to think about when is it reasonable, or when is this approximation good. But before we do that, let's just take a quick look at this example 8. So they say use a normal curve to approximate the probability that in 324 tosses, so that's quite a large n, not just 25, and a fair coin. Now the graph that we looked at just a second ago didn't look good until it was about n equals 25, but that's, you'll see, was because p was kind of skewed. P was only 1/5. But a fair coin, p is right in the center, so this is going to be a very good approximation. Maybe that's what we'll see when we try it. The number, and we want to figure out what's the probability that the number of heads is between this and this. Inclusive means including 171, including 180. So let's look at the solution. If y denotes the number of heads in 324 tosses, n is 324, then y is a binomial random variable with n equals 24 and p equals a half. We want to estimate then this, the probability that y is between these two values. This probability is the area between 170.5 and 180.5 in the histogram of y. Now the histogram of y probably is going to be very close to the normal in this case. This is approximately the area between this and this under the normal curve. You can see that it's not perfect, but the error is this part here, and this part here, and this part here, and this part here, and this part here. Those are the errors. Some of the errors underneath the curve, and some of the error is above the curve. We want, when we approximate, we're getting the area just under the curve. So you can see that it's kind of missing some and whatever. So we need to figure out mu and sigma for this random variable, but that's easy. It's just 324n times p a half, so that's that. And this one turns out to be, I guess, 9. So, sorry, it's 162 and 9. are the mean and the standard deviation. So now proceeding as in example 7, the normal we're estimating between here and here is the area between there and there, where x is normal with sigma equal to what we just said. So now we have to convert. So this is the question now. For x, then we want to convert this to z. So we take each of these values, and for example 170.5, and convert it to z by doing this minus this over that. You get it here, which gives us 0.94. Do the same thing for this one. Gives you 2.06. So this is for the normal. We want to figure out the probability that z, under the standard normal rather, is between 0.94 and 2.06. So that's this. And this we can do by the means that we illustrated before and that you're supposed to know from statistics. And turns out that the area is this. So therefore this is our approximation to this question, our original question. So it's 15.39. I'm sorry, 0.1539. And finally, we mention when is this appropriate to do this kind of approximation using the normal curve to approximate a binomial random variable. The idea of using a normal curve to estimate probabilities of a binomial random variable is based on the assumption that n is large enough so that the areas under the histogram are approximately the same. The areas under the histogram, in other words, the areas under the binomial random variable's histogram, are approximately the same as the corresponding area under the normal curve. But how large should n be to use this method of approximation? The answer to the question depends to some degree on the nature of the problem. However, as a rule of thumb, most statisticians only use normal curve approximations when npq is greater than 3. So let's see, what does that mean? So thus, if p is a half, n can be as small as 12, right? Because if p is a half, then q is also a half, right? Because p is the probability of success, then q is the probability of failure. So if one is a half, the other is a half. Then then if n is 12, we get a quarter times 12 is 3. So as long as that's okay in that case. However, if p is near 0 or 1, remember, if p is near 0, then q is what? Q is near 1, so it can be either way. So for example, we tried with p was 1/5, then q is 4/5. So then it won't be larger than 3 when n is 12. Or here they say, however, for example, if p is 9/10, then q is 1/10. Then in order for n to be greater than 3, well, this is going to be n times 0.09, so n would have to be at least as large as 34. So the rule of thumb is that npq should be greater than or equal to 3. Okay, let's look at some of these exercises. In each part, draw the histogram for the binomial random variable and with the given values of n and p. So here's n equals 3, p equals a half. No, we didn't do this, but so you might want to look at this and see, also think about how close is this to a normal curve after you draw it. So maybe this one wouldn't be good enough because they said n would have to be 12 in this case, right, when p is a half. But anyway, check it out and see what it looks like. Draw the histogram for this. In other words, by drawing the histogram, you have to find the probability that of x equals 1, x equals 2, x equals 3, and x equals 0 for this one. If it's b, you're going to have to do x equals 0, 1, 2, 3, 4, 5. Each of those probabilities, you have to do the binomial. So you might look it up in a table, or you could try the calculation. with p equal 0.2. Here's n equals 5, but p equals 0.8. Now notice that p equals 0.8 and p equals 0.2 should basically be very similar shape, but probably kind of mirror image of each other, or something like that. One will be high at the beginning and low at the end, and the other will be high at the end and low at the beginning. Okay, and n equals 10, p equals 0.6, so here you have to do quite a bit of work, but you could do it. Let's go to 2. Let x be the random variable whose histogram is shown here. So here basically it looks like x only goes up to 6, and assuming that it's binomial, or maybe they don't even say that here, they just ask what's the probability that x equals 2, so you just want the height here. What's the probability that x is between 1 and 4, so you want the height here, 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 and here, because it's inclusive, and you add them up. Probability that x is greater than 3, so that greater than or equal to 3, so that's this one, this one, this one, and this one, and x is less than 1 is this one, just the 0. Part number 3, in each part find the mean and variance of the binomial random variable with the given, so it's binomial, so to get the mean and variance you just use, we said np gives you the mean, and square root of npq gives you the standard deviation. Actually, they don't ask for the standard deviation, they ask for the variance, so it's just npq, not the square root. And you do the same thing for each of these. Number 4, in each part let x be the binomial random variable with the given values of np. Find the center of symmetry. And the inflection points of the normal curve that approximates the histogram for x. So here, they're really just, you have to work with the normal curve. It approximates this x, but it's not exactly the same as x, but they're not asking you for x, they're asking you for the normal curve. So the normal curve that approximates it is, we get mu is what? np, so it's just this number times this number. And the inflection points will be, you have to calculate the standard deviation, which is square root of npq, and then you take mu, which you've just calculated here, and do plus that and minus that, plus the standard deviation and minus the standard deviation. Those are going to be the inflection points. Remember, the inflection points are where the curve changes from facing downward to facing upward, or we said concave down and concave up. Number 5, find the following areas under the standard normal curve by using table 1 in the event. Okay, so then you're using a table. You can check a table on the internet. You don't have table 1 here in this book, but you can check it on the internet. Find the following areas under the standard normal curve. This is just working with normal curves. You're supposed to have done that in statistics. In each part, find the value of c that satisfies the given condition. This is still just about statistics, just about the normal curve. Same thing here. Number 9, use a normal approximation to find the following binomial probabilities. So y is binomial, but you're going to use the normal approximation. So here you have to go through the whole process that we described. Remember, you have to have the correction of minus a half and plus a half in the right places. Then you take a normal curve. You have to get the mean, which is given by, again, np, and you'll need the standard deviation, which you can get as npq square root, and go through all the steps. Find the following areas under the normal curve. So this is just, again, the same thing, finding area about normal curve. Give the normal distribution. Okay, same thing. Still normal curves. Using a normal approximation. Okay, so these are some word problems, so-called. So let's see. Assuming that a penicillin injection causes an allergic reaction in 1 of 10 people. Okay. Penicillin is an antibiotic. If it's injected, some people will get an allergic reaction. So 1 out of 10 people, or 1/10 of the people that are injected. Estimate the probability that fewer than 470 reactions will occur among 5,000 people injected. So we're gonna. This is a random variable. Remember, the trials are giving the injection to one person. The trial is giving the injection to one person. We repeat that trial with 5,000 people, or in other words, we repeat that trial 5,000 times. So n is 5,000, and the probability, we're going to say success, kind of strangely, we'll say success is a reaction, an allergic reaction is success. Okay, so that we can figure out what's the probability that that is less than 470. So so we want to work with the number 470. That is, the x is 470. Okay, so we're going to use a normal approximation to do this. This is a binomial situation, but we're going to use a normal approximation. So p is equal to 1/10. It's 1 out of 10 people will get the reaction. And sigma is what? 1/10 times 9/10 times n, which is 5,000, and square root of that. And then you get from that you can get a normal curve, because you know mu and sigma. Now you have to make sure that, let's see, we want to do 470 plus a half. And then you take that 470 plus a half and you convert it to a z variable, to a standard normal variable. And the way you convert it is you do what we've done many times. You take 470 minus mu and over sigma. And we've said that we could calculate those. So we do that. And then you'll figure out what 470 is, and you want to find the probability that you get less than that number under the standard normal curve. So you've converted this to a standard z, and then you figure out the probability for that standard z using the normal table. This one, a bag of 400 dimes, these are coins, is dumped onto a table. Estimate the probability that the number of heads is between 175 and 225. So again, this is a binomial. You could do it as a binomial, but they ask us to do the normal approximation to it. So again, you just figure out what's mu using the formula mu equals np, and you figure out what's sigma using the formula sigma equals the square root of nqp. I'm sorry, nqp. Don't forget the correction for plus a half and minus a half. So this would be 175 minus a half. This would be 225 plus a half. And then you can go forward. Let's see the next one. Assume 10% of the items coming off a production line are defective. So 10%, so P is probability of defective is 1/10. Estimate the probability that more than 14%. Okay, so you have to do this one. Be careful that this is percent. Actually, it shouldn't make any difference, I don't think. Okay. All right. Okay, that's it. Next one is Descriptive Statistics, and then one more section in Chapter 9 after that. Let's just read this very quickly, but we'll be doing another video on this one. So far in this chapter, the examples we have considered fall into two categories. The first involves an experiment, such as tossing 2 dice, for which the probabilities of the outcomes are determined using mathematical principles. In this type of problem, the mean and variance of the distribution are determined by equation 9 of section 9.2 and equation 5. Okay. The second type involves an experiment for which the probabilities of the outcomes must in some way be determined empirically, and the mean and variance must somehow be approximated. Consider the following example. Okay, so we'll come back to this in the next video.